Okay, folks, we're getting into some powerful stuff. I think this stuff is really exciting. I know this looks like a really short and inconsequential learning goal, know the fundamental equation. As it turns out, this is a pretty powerful thing we're going to go through. And I think it's in alignment with like unlocking the code of our thermodynamic universe. So we're going to start with this idea of the fundamental equation, which combines the first law and second law. So writing the first law, we have du equals dq plus dw. So that's our first law. Our second law says dq, and technically dq reversible, equals t ds. All right, that is our second law. And then also noting that dw reversible equals negative p dv. Okay. We're going to make this with respect to the canonical ensemble. Canonical. So that is our closed system. But we should note as we move further down the line, we're going to play this game with an open system, the grand canonical. Okay. So now combining these two ideas and noting here we're doing this for both reversible changes, we can say du equals t ds, okay, that's dq, minus p dv. And as simple as that is, there it is. That is our fundamental equation, okay? Fundamental equation. So why is this such a big deal? Well, what we see from this, what we learn here is u is a function of s and v. Okay, so we might not have learned that right away, but we can see that as it turns out, entropy and volume are the natural variables for internal energy. And we can play an even cooler game here, noting that u is a state function. We can play this game by looking at its full differential expression. So noting that u is a function of s and v, we will say that du is the following: the partial of u with respect to the partial of s at constant v ds, plus the partial of u with respect to the partial of v at constant s dv. And now I'm going to put this fundamental equation right here next to it, and we're going to see some pretty powerful stuff manifest. TDS minus P dV. And so now what we actually have here are the thermodynamic definitions of temperature and the thermodynamic definitions of pressure. So by definition, temperature is the partial derivative of internal energy with respect to the partial of entropy at constant volume. That's awesome. That is a better metric for temperature than temperature itself. And we can also see we get the thermodynamic definition of pressure. Here we can see pressure equals the negative partial derivative of internal energy with respect to changes in volume at constant entropy. That is cool. And so now, continuing along with this idea, noting that these are state functions and therefore must have exact differential expressions, we can come up with this thing that we call a Maxwell relation, all right? So I'm going to switch the order of derivatives here. And note the following. I'm going to say the second derivative of u with respect to changes in entropy and with respect to changes in volume equals. So now we've got to do that derivative for temperature. So that's going to be the partial of T. Now that's going to be with respect to V at constant S. So we switched that order. And then we also note that I can switch the order of this derivative. I have the same thing, second derivative of u with respect to s, with respect to changes of s and v. And now that's going to be the negative partial derivative of p with respect to S at constant V. And thus we have obtained our first Maxwell relation. Okay. These are what I really do think of as the code of our thermodynamic universe. Okay. So let's do another one. This time, let's do that with respect to the free energy with Gibbs. Okay. So we'll start by noting that Gibbs is H minus Ts. And noting here, trying to figure out what are our natural variables with respect to G, we'll take derivatives of both T and S. Okay, so that will equal dH minus T ds minus S dt. So we can also play that same game with H, noting that H is by definition U plus PV. And looking at the derivative of dH, that's going to be du plus dPV. So, right, continuing along, that's du plus P dV plus V dP. And now we're going to plug that in over to here, okay, into dH. So now dG equals du plus PdV plus V dP. Okay. Let's see, making sure that I'm following along. Minus T ds minus S dt. Okay, so now we also remembered, though, from the fundamental equation that du also equals T ds minus S dt. So plugging that in, right, you can tell that this is important stuff when we're plugging in like everything we know into the same equation, all right? So now we get T ds minus S dt plus P dV plus V dP, okay? Oops, I said du is TdS minus PdV. I knew I was doing something weird, okay? Du is TdS minus P dV. Apologies. So that came from what we did above. So let's make sure that I'm following along. I'm not going to edit this out. We're just going to go for it. So dG equals du, which is TdS minus P dV plus PdV plus VdP. So you can see where this is going, right? And then now we have a minus TdS minus S dt. Okay, so now we can start canceling like things. So TdS and minus TdS cancel, minus PdV and positive PdV cancel. So now we're left with dG with respect to its natural variables, V dP minus S dt. And lo and behold, here is another version of our fundamental equation. Okay, so we can have the fundamental equation with respect to all of our thermodynamic potentials, provided that we've applied this using the first law and second law of thermodynamics. So now we can see that G is a function of P and T. And we note that G is a state function. So if we look at its total differential, dG, that will be the partial derivative of G with respect to P at constant T dP plus the partial derivative of G with respect to T, all at constant P dt. And once again, playing that same game, we'll put the fundamental equation under there, V dP minus S dt. And you can see now we arrive at other thermodynamic definitions of volume and another way that we can think of as a thermodynamic definition for entropy. So for example, we can say volume now equals changes in Gibbs with respect to changes in pressure at constant temperature. And another way we can view entropy from a thermodynamic point of view is the negative changes in G with respect to T at constant P. Super cool. And now similarly, right, Noting that these are state functions and have exact differential expressions, we can switch the order of the derivatives. So looking at the second derivative of g with respect to p and t, okay, so we'll do that with volume first. So we have that with respect to p. Now let's do it with respect to t. So now that's going to be partial of v with respect to the partial of t at constant p. And that will equal the negative partial of s, let's see, okay, I did t over here, now we do p, with respect to p at constant t. And here we go, boys and girls, another Maxwell relation. Okay, so as it turns out, there are 4 Maxwell relations and 4 corresponding versions of this fundamental equation, and here they all are, right? So we did this explicitly for U and for G, and right here are those relationships, but you can see we can also play the same game with enthalpy and also with the Helmholtz free energy. And these relationships are powerful. We can do lots and lots of things with these relationships, which we will do in time. And what I also want to note here, this looks intimidating, like how am I ever going to remember this? Well, in the next video, I'm going to go through a really handy, useful thing known as the thermosquare. I will see you then.